Okay, and we're talking about the assessment, the sample assessment I gave you guys to work on while you were um, for the test coming up, either Monday or Tuesday. So I don't know what I need to explain here, but I'll try. Basically, you're taking the cube root. If you take the cube root, first thing you want to do is see if the things that are in the underneath of the cube root can be reduced. So if you type in 162 divided by 3, you will get 54. And the negative can already be pulled out because taking the cube root of a negative is a negative. And then x to the ninth divided by x gives you x to the eighth. Alright, so now remember that we're looking for groups of 3. Our index number is 3, so we'll be looking for index number 3. Okay, so we take 54, we break it up into any way we can. I broke it up between 9 and 6. I broke 9 and 3 and 3, 6 into 3 and 2, and I broke up my 8 x's into 8 x's. So then I circle groups of 3. So I circle the group of 3. When I do that, I bring it out. Take out a group of x's, just like they were numbers. So I take out a representative, which is an x, and I have another x, which why I make it x squared. And then I write a cube root, and then I write down what are the things that I did not circle. I did not circle a 2 or an x squared. I put that underneath the square root, and I'm done. And I repeat this process for either division or a multiplication, or just even simplifying. Here, number 2, you just have to make sure that you do groups of 4 and pay attention to the index number, that tiny little number on the far left, because that's very important. Do your factor tree for the numbers, and then again the letters, you just want to make sure that you can take groups of 4 out. X doesn't have enough, so you would leave x squared underneath. Y to the fourth has 4 that'll come out, that's why you have a Y. Z has 4 that can be come out, but then you still have 3 left over. Okay, so again, I write what I had that I'm taking out, represent the representation down here. I can't do anything with that other than write it, and then I leave the fourth root of whatever stuff I couldn't take out, which would be the stuff over here, the 12x squared z cubed. So again, I would do that for 3. I would do that for and then 4. I would divide these two, and then I'd be left with the square root of 25x to the 6th, and then I would just do 5 and 5 for 25, so 5 comes out. And then I'd have 3 groups of x's, groups of 2, 3 groups of 2 that I can take out, and I wouldn't have anybody left over. When you go to do multiplication, remember that when you're doing a multiplication problem, everybody's working together. So it's like this is like one big huge factor tree, and you're still looking for groups of 4. See the 5 that's sitting there, that's already out. Now you're looking for what can you take out of 2, 6, 9, and 3. One method is to multiply all of them together and get 324 and break it up again, or just leave them as is and you just leave the 2 alone. 6 change to 2 and 3, 9 change to 3 and 3, and you have that extra 3. You can do that, and basically then you have to you end up having to just break it up. It'll look like the factor tree anyway. Then you take all your x's and collect them up, and then see what you can pull out. So there, as in a multiplication type problem, you're basically just working as a team. You're trying to get everybody out of what you can, and then whoever's left just gets kind of plumped together. Multiply the big numbers if you have any left on the inside, and then leave your exponents. Just combine with exponents. Okay, number 6 is adding and subtracting. When you do adding and subtracting, so is 7. You want to make sure you do combine like terms, so you have to make sure that what's underneath the radical is the same. In this case, we have a cube root of 4x squared. We have another cube root of 4x squared, so together we have 6 minus 4. So we have 2 of those cube root of 4x squareds. And then this last one, the one on the end here, we can't do anything with, so we just carry it down, sort of like combining x's and y's. This was like 6x minus 4y plus 2y. I mean, excuse me, 6x minus 4x plus 2y kind of idea. And you just kind of write what's if you can combine it, great. If you can't, then you just write it kind of tailed on there. Same thing with 7. The only difference with 7 is some simplifying that had to be done, and I show that in this step. These are all my simplified stuff, and so when you do your factor tree and you simplify all that, then you combine like terms, and you can see I can put that 24 square root of 2 and that 45 square root of 2 together. And then that square root of 3 I can't do anything with, so I just kind of bring that thing down. With number 8, my suggestion for number 8 is to do a table and fill in the values. And then once you get done, write them out long ways so they look like problems 6 and 7, and then clean them up just like you would do 6 and 7. Number 9 is distributive property. Just remember, inside numbers can't get mixed with outside numbers. So 3 times the square root of 2, since they're one's inside, one's outside, you can only put them next to each other. And then you're just basically cleaning up. That's all you're really doing on all of these. Number 10, same thing, adding and subtracting. You got to make sure you combine like terms. Be careful. This says cube root, this says fourth root, this says cube root. You can't mix cube roots with fourth roots. So just be careful. That's all. 11, 12, 13, 14 is you just rewriting stuff. Remember that it's power over root. In this case, they have the same root. That's why it's a 5. And then we have x to the first and x squared. Put them together, and remember, when you multiply, you add your exponents. So your answer is the 5th root of x cubed. Number 12, do the same thing here. We take the cube root of negative 27. Remember that this x to the minus 9 flips down. If you notice, that's why it's positive, but it's underneath. And then you take the cube root of the top and the cube root of the bottom. And that's how you'll get the answer to number 12. Number 13, again, they all have the same root, so they all have a square root. Remember, if you don't see it, it's a 2. All these guys, the 7 to the first power, the x to the 5th power, and the y to the cubed, all get put underneath a radical, and then you got to clean it up. Number 14 does not have the same root, so you have to get them with the same root. So the first they have in common is 21. 3 and 7, first number is 21 in common. So that's what I have in red here, showing how to change them into 21s. So now I have this, and now they have the same root, so I can put them under the same root, and then the powers I get listed under it. Okay, let me change to the next page. Hold on a second. Okay, so now we're doing the functions. Let's see. So we got 4 functions, doing different things with them. Alright, number 1, g plus f of x means you're adding the 2 functions. We're not plugging anything in, so in the game it would be like me handing you the card and you not doing anything with it. So I literally substitute g and f next to each other. See, here's g over here. Here's f. It says to add them together, so literally that's all I did, and combine like terms. That's all you got to do. Number 2, I took the 2 functions, and it says that big dot, that big black dot there means multiplication, so I'm going to literally multiply my 2 functions together. So I take g and f and multiply them together and clean that up. Number 5, this operating on is like you playing that game where I pass you the 2 to the f function, then f uses it, gets an answer, and passes to the g function, that game we played. So you find f of 2, again the letter closest to the number is the one you're going to use first. You plug it into f's function, which says to take 4 and multiply it by whatever it gets. It's given the 2, so you have an 8. The 8's now handed off to g, and g plugs it in its function and does the math on that and gets 56. Number 6 does the exact same thing. It's noted a little slightly different because there is 2 ways to write a composition. But again, the idea is whatever letter is closest to the number or to the letter is the one you use first. Since g is closest to 3, 3 gets put into g. Let me just pop it up here. I'm going to put a 3 in up here. Remember, you replace x with the number. Okay, so I get my answer, which is 6, and then I pass it on to f, and then f just multiplies it by 4 because that's its job, and you get the final answer is 24. So keep going. Number 3 down here, it just says subtract the 2 functions, and if you can't do anything with that, you just leave it as is. Number 7 says take g's function and plug it, or take x and plug it into g. Well, that's already been done. So then after you do that, you plug into h. So you take everything that h does, which if you go up here, h is just saying take whatever comes in, multiply it by 2, and subtract 1. If you look down here, that's exactly what I did. I multiplied the function by 2, and I subtracted 1. Remember, you replace x with whatever comes in. In this case, x squared minus x is coming in. You replace x, h is x, with x squared minus x. and that's how you get this. Remember, this is just combining distributive property and then just mix it with the 1. And again, this is just more practice. This says take a half, put it into G, which I did here, and then I got -1/4, and then I handed -1/4 to K, and K put his or her or its, whatever, -4 into its function and got an answer. In number 8, it says G operating on G. That means G is being used twice. So you're going to take G's function and plug it into itself. So basically, remember, it's supposed to square x and subtract square x and then subtract x. So if you look at the function, here I have whatever came in, which in this case is itself. I squared it and then I subtracted it. Okay, and then this is cleanup. It's not a lot of fun with this. There's a lot of FOIL problem here. A little subtraction over here. Be careful because you got a minus sign that has to be distributed. That's why this minus a minus x becomes a plus x. And then you clean all this up. Alright. Determine whether or not they're inverses. Basically, you're plugging each other's functions into it. You're basically taking turns putting G into F and then F into G. And if you don't get X, then they are not functions. And since it doesn't, looks like when you put G into F, you don't get X, so they are not inverses of each other. Same thing here. I put G into F, so I literally take this whole thing and plug it in for X over here. And I see and if I clean it up, I do get X, and then I would do the opposite. I would take all of this, plug it in for this guy's X, and see what happens. And I get X. So that means they're inverses of each other. Another way you could try to do it too is you could try to do the inverse, like down here, where you switch them and rewrite them. Okay, find the inverse of the following functions algebraically. This is when you switch x and y, and then you solve for y. That would be how you do that. And I basically all the steps are here. I really can't, I don't want to go sit there and go through all these, but you can look at the steps. The big thing is you switch x and y, and then solve for y again. Get y by itself again, and that's how you do those. A little complicated, but not too bad. Now, if you want to, you could actually use the flowchart, which go look at my videos, and you can see how the flowchart's done. You could do flowcharts as well. I'm going to give you that option either or. What else? Okay, true or false. If f of 2 is 9, then the inverse of f of 9 is 2. Again, that's true because the domain and the range swap places. F of x and the inverse of f of x are reflections over each other over the y equals x. Yes, that is true too. You can actually see the picture here. The inverse of a function is always a function. No, that's not true. The good example of that was when we got x squared, and then when we drew its inverse, it did not pass the vertical line test. The what does that say? The inverse of the function is always minus x. No, we want to get x, not negative x. We want regular old x. If the domain of the function is where x is greater than or equal to 3, then the domain of the inverse would be x is greater than or equal to -3. No. We want to say that the range of it is that. Oh no, that still wouldn't be true, because then this would have to be the same thing. So. Okay, determine if they're inverses. All you have to do is draw your y equals x line. It's not reflect over y equals x. That would be a perfect explanation. This one says if I have the inverse, basically I have to pick a couple of key points off that graph and just swap them and graph them again and see if it reflects over the y equals x line. That's pretty easy. Here it says Lewis has the following work shown on his homework. F of f prime of 6 equals 10. Why is this wrong? Because if they were inverses, the f of the function of the inverse of 6 should be 6. Okay, because they're supposed to undo each other. So if whatever comes in will come out to be the same if you plug the inverse into its function. And I think that I gotta switch over to my graphs. Hold on a second. Okay, here are my functions that I have to work with. I have the square root of, the negative square root of x plus 1. Again, if this were starting off as the square root of x, its parent graph would start at 0, 0. But because I have x plus 1, I'm going to shift the graph to 1 to the left. So I'm going to start off at -1. And if you see, my domain starts off at -1, and as x gets bigger and bigger and bigger, I still get a graph. If I go below -1, I don't get any graph. So that's why the domain in this says x is a member of the real number system, and x has to be greater than or equal to -1. You can't pick any x's smaller than -1 because there's no graph here at all. In the range, if you notice, the smallest value, or excuse me, the largest value, because this thing is going down, the largest value I have is 0, because this is -4, 0, this point. And then from then on, y starts to get smaller and 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 smaller. So the range would be all real numbers where y is less than or equal to 0. Now, the other things are just you just looking at them. The 0 would be -1. You can write it x equals -1 as a 0. Remember, these are places where you hit the x-axis. You write as an ordered pair when you do an intercept. We put that in because the SOL sometimes asks you about zeros and sometimes asks you about x-intercepts. Y-intercept, you would just look where it hits the y-axis. You can see right there. If you can't see it so easily, what you can do is go to your table where you've plugged in the graph, and you can just look up 0, and -1 will be right next to it. Where is this thing increasing? If you can tell, it's not increasing. The entire thing is downhill, so you won't have any increasing. And then the entire time this thing is decreasing except where you start. So that's why it decreases from -1 to infinity. We don't count -1 because when you start off a ride, you're not increasing or decreasing. You're kind of sitting up here at the top of the hill. All right, end behaviors. Let's see if I can keep the graph on there. Okay, as x gets really, 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 really big. So basically, you're sliding along the x-axis as x gets bigger and bigger and bigger and bigger and bigger. Well, what's y doing? It's getting smaller and smaller and smaller and smaller and smaller and smaller. That's what this means. As x gets really, 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 really small, well, x can't get really, 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 really small. It can only get to -1, and that's it. So there's no like left arm over here. There's nothing over here for us to talk about. So that's why it's not applicable. All right, it's the last one. We got to go over this one. Okay. Whew. All right, so we have a parabola, a quadratic equation. The graph is called a parabola. Basically, it's like where is it that we can put in x's? Well, it's kind of weird because you think that x can only go so far, but really this graph is going kind of off to the right here, but up and off to the right. So even if you named a point right here, yes, it's not on your graph paper, but it's up there. So you can pick any x's you want, and it's going to give you a graph that's right above it, or in some cases, like right in this little section, it'll be below the x-axis, but the rest of them are above the x-axis, but you're still going to get a value. So the domain is all real numbers. That's what that means. And the range, well, the range doesn't have that kind of flexibility. Y can't just be whatever it wants. It can come all the way down here and be -2, but then it goes right back up again. So y, or excuse me, -3. Y can only be -3 or bigger. See how it goes down, hits -3, and then comes back up again. So y can only be so small. Now the zeros, again, what you would do on that is you would do, to find your zeros, is you would intersect with the y equals 0 line. Remember we did that? We used the intersect key. The first curve you put in is here, and the second y2 you put in y equals 0. Hit the intersect key, and it should pop out each one of these two values. You just guess. Remember, you guess at -2, and then it'll give you the -1.73, and then you would do that intersect key again, and then you would pick +2, and then it would give you the +1.73, and then again, this is just written as intercepts. The y-intercept obviously is 0, -3. I'm hitting right there. That's fairly easy to do. Now, where is this thing increasing? Now, the weird part is you think both pieces are increasing, but it has to do with you being on the ride, and you start from the left and ride to the right. So here, if I'm starting up way up here, I'm going down, I'm decreasing, and then when I hit here, I kind of like don't do anything because I'm stopped there, and then I go back up again. It's like really, really, really crazy roller coaster. I've started up here, gone down, hit a spot, and then come right back up again. So I increase when x is 0. See, that's, you're looking at the graph to decide when is it going up and when is it going down, but you're supposed to be telling me what x's is that doing that. So right here where this x is 0, it's not doing anything. But as soon as x jumps off the 0 point, as you compute x's with all these numbers, this thing is going and increasing. So increases while x is going from 0 to infinity. It means as big as x gets, this thing is going to keep on growing and growing and growing. Now on the decreasing, that means as x, basically as x is going, starting off from way over here and going and going and going and going, and it's decreasing. It decreases while x goes from negative infinity to 0. In other words, as soon as it hits 0, it starts going back up again. So it's going to decrease the whole time. So like even when it's way out here and out there in the boonies, it's negative like 1,000. And if you get stuck, you can always look at some of the values. Like go out there and some really high values and see what's going on. All right, end behavior. Okay, end behavior is what's y doing. So this is, again, this infinity thing. The positive infinity is talking about the right arm, and the negative infinity is talking about the left arm. Kind of picture this as like a stick figure, and these are two long arms, and the hands are the arrows. Okay, so as x gets really, really, really big, so as x goes really, really, really big, y gets really, really, really big. Okay, as x gets really, 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 really small, it's going this way. What's y doing? Y is still getting really, 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 really big, and that's where the two infinities come from. Whew, all right, we're almost done. Okay, using the functions above, find g of f of x. Okay, so they wanted you to plug f, remember f's the one closest to x, f into g. So if you plug f into g, so we're going to take f, all of this piece right here, and we're going to put it in for g. So it's kind of interesting because this is a square root, and you're about to square it. So remember what happens when you square a square root? It goes away. So if you square a square root, notice it goes away. We talked about that before. The negative goes away because when you square a negative, it becomes positive. And then you still have the minus 3, which gives you x minus 2. Using the functions above, find f of g of negative 1 square root of 5. Well, if you already know, now I think this is kind of, alright, so what they want you to do is find f of g, or excuse me, f operating on g is negative square root of 5. This is where you would go in and put negative square root of 5 into g. So you go over here and put it into g, get an answer, and then hand it over to f. And I think I kind of showed you this. See, negative square root of 5, you square it, minus 3, that gives you 2, and then you turn around and hand your partner the 2, and then they do something with it. They follow their function. Using the functions above, find g inverse. Okay, so they want you to take g's function. They want you to find the inverse. So you can either do that with flowcharts or where you write out the steps and go backwards. Again, see that video if you haven't already. And then if you don't like that, you can do it the algebra way, which is what I was doing somewhere on one of these other pages. Okay, again, there's videos to show how to do it. Same video will show you how to do it algebraically as well. Well, I hope this helped.